This is the test review guide for Algebra 2, Unit 5, answer key video. So the first two problems ask you to use synthetic division to divide these two polynomials. Remember that whatever divisor you're given as a linear factor, you want to divide by the opposite number. So here we're going to be dividing by -7. The next thing that you want to make sure that you do is check to see that if you've got a polynomial as the dividend, that it's in standard form. That means that I have x to the fourth, x to the third, x squared, x to the first, and no x down there. And that each of those terms is accounted for, not only in order, but that none of them is missing. And in this case, that is true. And so then the next thing we do is we write out the coefficients. Because x to the fourth doesn't have a written coefficient, the coefficient is 1, 6, -4, 19, and -14. And we're dividing by -7. And remember that you want to leave space to write another row of numbers inside your box. And so you take that first number and you don't do anything to it, you just bring it down. And so I'm going to bring down the 1, then I multiply 1 times -7, and I write the answer, which is -7 here, and then I'm going to add down the column. 6 plus -7 is -1. I'm going to multiply again, -1 times -7, this time is +7. -4 plus 7 is 3. Again, I'm going to multiply 3 times -7, and that's -21. 19 plus -21 is -2, and -2 times -7 is +14, so your remainder is 0. And help yourself visually by putting a little box around the 0 to make sure that you know that that remainder is written as a separate thing than the rest of the polynomial. And if the polynomial that's given to you to divide is 4th degree, then your answer is going to start with the 3rd degree. So when I write out my quotient for this, I'm going to have 1x to the 3rd minus 1x squared plus 3x and then minus 2. And there's no remainder here because it's 0, and so that's my answer just like that. Excuse me. So the next division problem that I have here, notice that I start with x to the 4th, but there's no x to the 3rd term. So here I'm going to need to put a 0 to stand in for the x to the 3rd term, and then x squared, x to the 1st, and no x there. And then I'm dividing by +2. So 1x to the 4th, no x to the 3rd, -9x squared, 13x to the 1st, and minus 8. And I'm dividing by +2. Bring down the 1. 1 times 2 is 2. 0 plus 2 is 2. 2 times 2 is 4. -9 plus 4 is -5. -5 times 2 is -10. 13 plus -10 is +3. +3 times 2 is +6. And -8 plus 6 is -2. Put a box around that. That's your remainder. Again, we started with x to the 4th, and so our answer is going to start with x to the 3rd. So it's 1x to the 3rd plus 2x squared minus 5x plus 3, and then it's going to be minus, and then a fraction, and you're going to get your fraction from the remainder here and what you were dividing by up here, that polynomial or that linear factor is going to be the denominator of your remainder. So the remainder here is the 2 over x minus 2. And yes, you need the minus, you need that minus right there to show that your remainder was negative. And so my whole answer is x cubed plus 2x squared minus 5x plus 3 minus the fraction 2 over x minus 2. Now, remember that when you're asked to classify something by degree, you're looking for the highest exponent. And so in this polynomial here, 5 is the highest exponent, and so the degree is 5th degree, but remember that I want you to know that word, and the word for 5th degree polynomial is quintic. The next question asks you to decide which of these graphs has a function, is the graph of a function of even degree. And remember that it's even degree if the ends, the right and the left end behaviors, the ends are the same. That means that they're either both up or they're both down. And so of all of these function graphs here, the ones that are both up or both down are here and here and here. And these other two I didn't circle. This end is down, this end is up, this end is down, this end is up, so neither of those can be it. Those are the three that have both ends up or both ends down, so they would be polynomials of even degree. So you're going to make up the graph of a polynomial of odd degree. And that just means now that the ends are going to be different. So for odd degree, you want the ends to be different or opposite. So one end is going up and one end is going down, and it doesn't matter which, right? You're going to have ends that are different, and just do some waviness in the middle, and that is a polynomial that would be of odd degree. Now, number 5 is asking about transformations. We didn't talk a lot about this in class, but it's exactly like we've been doing transformations all along. If you start with the parent graph of x to the 4th, which is basically like the quadratic graph but steeper, this equation says move it to the right 2 and up 1. So take that graph, move it to the right 2 and up 1, and give it the same exact shape. And that is your graph for that one. And then number 6, the parent graph of y equals x to the 3rd power looks something like this. And so in this problem, we are going to move this to the left 4. Oh, look, I forgot something. Right here, that means that it's going to be flipped. So instead of up on the right and down on the left, it'll be down on the right and up on the left. Then left 4 and down 2. And so this graph, shifting it left 4 and down 2, means that the center of the graph is going to be here. And then you want that flip, so it's going to go down on the right and up on the left. Now grab your calculator, and for 7a and b, you want to substitute into the polynomial the x value that's given. So you're going to substitute for this one positive 4, and it says show the substitution. So you want to show f of 4 equals 2 times 4 to the 3rd power minus 5 times 4 squared plus 4 minus 3. Type that into your calculator exactly like that. Don't try to fix it or change it or compute things ahead of time or do some of it in your head. Just type all of that into the calculator and f of 4 equals 49. Remember that anytime you're substituting x value that's negative, like -2, into an expression that has exponents, you want to use parentheses. You have to use parentheses when you type it into your calculator. So let's write it with parentheses. We're finding f of -2, and the substitution is -3 times -2 to the 5th power minus 5 times -2, and then plus 7. And then type all of that into your calculator, hit enter, and you will see that f of -2 equals 113. So this next problem, again, I had said that we didn't do much with the transformations in class because you know these already. Just keep in mind that the exponent doesn't have any impact on the transformations. The only thing that you want to think about here are the vertical stretch or compression. If there's a flip, this one doesn't have a flip. Any shift left or right, and then, any shift left or right, and then I'm running out of colors here. How about that one? And then any shift up or down. And so maybe I can even match the colors with the writing. So this one has 3 transformations, and that's what the directions say, 3 transformations for each. And so the 3 out in front is a vertical stretch, but remember that you have to write the factor. So it's a vertical stretch, factor 3. And it's a stretch, not a compression, because this number is bigger than 1. If it were a fraction or less than 1, it would be a vertical compression. And then the plus 57 is going to be a shift to the left by 57. And then that minus 392 is going to be a shift down by 392. In part B, again, there's three transformations. The first thing that you see is a flip, and then the second thing that you should see is the shift to the right. Remember that the exponent doesn't have any kind of a transformation associated with it. And then your plus 876 at the end is a shift up. And so here we're going to say that there's a flip over the x-axis. And that there is a shift to the right, 78, and that there is a shift up, 876. And remember that I do expect that you use the words shift, flip, x-axis, and don't write plus or minus, but write up, right, down, left. And finally, in letter C, I see this flip, and I see this shift to the left, and I see this shift down, and that 91 doesn't have anything to do with any of those. So the minus out front is that flip over the x-axis. And the plus 538 inside the parentheses, remember insiders lie, so that is a shift left 538. And then the minus 74 is going to be a shift down 74. Now, if you wanted to do the next problem without even graphing this in the graphing calculator, you could do that with the transformations. First of all, x to the third power, that's an odd degree, which means the ends have to be different. Well, in this one, the ends aren't different. So it can't be this, and it can't be this. And x to the third degree could have two turning points, or it could have what I've called it like a little twist tie, which is, ooh, I clicked some weird thing, which is, when I say the twist tie, that's this little thing right in here. And remember that adds to the degree. Whereas this is definitely linear over here, so that's not what we're looking at. This one with the twist in it, that has shifted up one, and it's x cubed. So it's the first graph. And number 10 asks about a shift left 2 and down 7. Remember that insiders lie, so left is going to be something like x plus 2 inside the parentheses to the third power, and then down 7 is going to be minus 7 outside the parentheses. And the only one that has x plus 2 and minus 7 outside the parentheses is choice B. Now, for number 11, if I were you, I would grab my calculator, I would graph this, and then step back and take a look. And your graph of this should look something like this. It's a very rough sketch, but it's asking you the range of the function. And so what you want to do is find what is the highest y value, and so find that maximum, and that's a 5. And so the bottom of the graph is negative infinity. The top of that graph is y equals 5. And so the range is going to be negative infinity to positive 5 inclusive. Now, on your test, there's going to be questions that aren't going to be super obvious if you try to graph it in your calculator. So if you graph this in your calculator, you may not be able to tell the end behavior, but you don't really need to. Because if you look at the leading coefficient is negative, that means the right end of the graph is going down. And if you look at the end behavior is, or the degree is odd, 79 is an odd number, the ends are different. So if the right is going down, the left would have to be going up. Let's try that again. You don't have to try to graph this one. All you have to do is look at the leading coefficient. The leading coefficient is positive, which means that the right end goes up. And the exponent on the leading, in the leading term is even, which means the ends are the same, so they're both up. Now in this problem, you see that the question is asking about the domain and range, and the domain for every polynomial function is going to be all real numbers. So it can't be A and it can't be B. And for this problem in this graph, it's on the left it's down at negative infinity, and on the right it's up at positive infinity, and it doesn't have any breaks in between. And therefore your range is all real numbers also, and so your answer here is D. In this next one, you really don't need to put this in your graphing calculator because this equation is this graph. And the couple of things that you want to talk about, first of all, is that the only turning point here is this point right there. Let's say that that point is 0, -3. There are no other turning points. But, and I know that you're not asked this question, even though there's only one turning point, because of this inflection right here, that little twist tie thing, remember that adds to the possible degree. Well, in a normal function with one turning point, that would be degree 2, but because of this inflection point, this has to be at least degree 4. Why not 3? Well, because both ends are doing the same thing. If both ends are going up, then it has to be an even degree. Like I said, you weren't asked that, but that's just a little bit of an analysis of that graph. What you are asked here is to see if there's any local maximum. Well, this down here is a minimum, and there's no other turning points, so this is going to be none. We said that that was a minimum, and so the minimum is 0 and -3. And remember that even though you have that little twist tie there, that doesn't change the increasing, decreasing. So in this graph, it's decreasing here. And I know that some of you like to write the word decreasing. I don't know if I can do that on my iPad. Let's see. So this is decreasing here, and it's increasing. It's increasing over here, and it doesn't change through the inflection point. So it's still increasing, it just slows down. So it's not a difference, it just slows down. And so that's going to be increasing through there. Increasing all the way through there. And the increasing and decreasing change at x equals 0. So it's decreasing from -infinity to x equals 0, and it's increasing from 0 to x equals +infinity. Next we have our famous box problem. And so let's take a look at this graph. I've given you a crazy graph. It's probably not going to be so crazy on the test. And I want to kind of think about the turning points. I see 1, 2, 3, 4 turning points. Number of turning points, let's already write that in there, is 4. And if you want to get really super picky, this is a min, and this is a min, and this is a max, and this is a max. Mins are at the bottom of a valley, maximums are at the, maxima, sorry, is the appropriate word. Maxima are at the tops of hills. Now, the function family itself is polynomial, and remember that if you forget that, just look at the front of the test. Up by where it says name and you've written your name, it'll say test polynomial functions. Now, since there's four turning points, the probable degree for this polynomial is 5th degree, but it says classify. So don't just write degree 5, okay? You're going to actually write the name of a 5th degree polynomial and say quintic. And if you really want to show me that you know what you're talking about, put 5th degree. But I'm looking for the word quintic here. The domain of all polynomial functions is negative infinity to positive infinity. And because this one goes all the way up to infinity and all the way down to negative infinity on the y-axis, your range is also all real numbers. Now your increase and decrease is where it gets a little bit crazy. So I see 3 places where it decreases, and I'm highlighting those red. And then I see 2 places where it increases, and I'm highlighting those blue. And remember that increase and decrease you want to give in terms of x values. So the x value here I would say is about negative 1.5. And the x value here is about x equals positive 1. Those are the 2 mins. And then the maxes, let's say x equals negative 1/2 or negative 0.5. And x equals positive 2. And so my first interval of increase is this guy right there. That goes from negative 1.5 to negative 0.5. And then my next interval of increase is this one right here, and that goes from positive 1 to positive 2. And then my decrease, my intervals of decrease, the first one is here, and it goes from negative infinity to negative 1.5. And then my next interval of decrease is this one right here, and that goes from negative 0.5 to positive 1. And my last interval of decrease is way over here, and that goes from 2 to positive infinity. Now, my x-intercept, I'm going to have to erase some of this stuff. So let's get rid of all the scribbling on the graph that I've done so far and look at x and y intercepts. So I see x-intercepts here, 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 and here. And make a special note to yourself that this one is different because it's a bounce, and so the multiplicity here is 2. And so if you really want to show off, tell me that the zeros are at x equals negative 2, negative 1, 0, and then give me the bounce that's the double root as 2 and 2. And take all those numbers, the negative 2, the negative 1, 0, and 2, and write those as ordered pairs. Those are your x-intercepts. Negative 2, 0, negative 1, 0, 0, 0, 2, 0, and 2, 0. Notice that your y-intercept is also an x-intercept. And so in this case, your y-intercept is 0, 0. And those maxes and mins that we said were the 4 turning points, these maxima, let's say that's negative 0.5 and positive 1.5. And this one here is 2, 0. So those are maxima. And I apologize, I shouldn't have put those words local. I told you we weren't going to do local. So your maxima are negative 0.5, comma 1.5, and then 2, comma 0. And negative 1.5 negative 3.5 for the first minimum. Sorry, I didn't put that on the graph. So negative 1.5, negative 3.5 is there, and then this one would be about 1, negative 4. So 1, negative 4. And for the end behavior, the right end is going down, and the left end is going up. So in this next question, just remember that we've used several words that mean approximately the same thing. X-intercept means more or less the same thing as root, as solution, and as zero. And so here another word for x-intercept then would be root. For number 18, remember that the word complex here, in fact, I'm going to make this note over here. Complex solution, solutions include all solutions, both real and imaginary. So the number of solutions that any polynomial has is equal to the degree of the polynomial. And so there are, and I don't know if they're real or if they're imaginary until I look at the graph of the polynomial, but in this case there are 3 complex solutions, meaning that there's 3 solutions altogether, including all the real and all the imaginary solutions. In number 19, I see 3 places where there are x-intercepts, here, here, and here. But remember that this one and this one, because they bounce, are double roots. So this is a double root, multiplicity of 2. And this is a double root, multiplicity of 2. And so count those twice. So here's x is negative 1, x is 0, and x is positive 1, and you're going to write the double roots twice. So what are all the zeros of this function? Negative 1, 0, 0, positive 1, and positive 1. In this graph, notice that you see 3 x-intercepts here, here, and here. But in the middle one, because the twist tie shape happens right on top of the x-axis, that is a triple root. And so you're going to write that 3 times. So if this is x equals negative 2, and this is x equals 1, and this is x equals 4, I'm going to write that triple root 3 times, negative 2, 1, 1, 1, and 4. And just another picture of some double roots. You've got a double root here, and you've got a double root here, and the question is asking you just to identify the double roots. And I did not mean to make that look like a smiley face, but it does. So there, and so your double roots. Wow, it is late and I'm tired. Double roots at x equals 0, where the smiley face is, and at x equals 2. So linear factors are always going to be it looks like it's a factored polynomial. So linear factors, for example, would be things like x minus 2 or 3x plus 1 or something like that. And so, etc. And so those aren't the answers to this problem, but that's what it's looking for when it asks for linear factors. It's not asking you to multiply anything, it's just saying what are the linear factors. And so in this case, you want to say that the linear factor here is x plus 2. Remember, it's always the opposite sign. And your thinking here is because x plus 2 equals 0 gives me x equals negative 2. That's where the negative comes in. And so x plus 2, and then it's just x when the solution is 0, or x-intercept is 0. And then this one, you're not going to write x minus 5/3. What you want to do is think of where that 3 would go. I'm going to give you 3x minus 5. But if you think about this, in backwards, 3x minus 5 equals 0. So 3x equals 5. And then divide both sides by 3, and x equals 5/3. And it would be best if you would write that whole thing as a function. And so you could say something like x times x plus 2 times 3x minus 5. And that's not to say that there might not be a leading coefficient or another number multiplied in there or a negative. So it's not f of x equals all of that. But those are the linear factors that would give you intercepts at negative 2, 0, and 5/3. And then the next problem, number 23, is just backwards. The next problem gives you the factors and asks you to give the x-intercepts of the function. So I would, if I'm thinking through this and I'm not sure, I would just take each of these and set it equal to 0. Equals 0. 5x minus 4 equals 0, so 5x equals 4 and x equals 4/5. X plus 1 equals 0, and so x equals negative 1. X minus 3 equals 0, so x equals positive 3. And you don't have to show all this work if you can do some of it in your head. But that's where these numbers are going to come from, x equals negative 17. And so your answer to this problem would be 0, 4/5, negative 1, positive 3, and negative 17. And so you're going to kind of do that same thing here. And what I want to do first is just the factored form, and then I'll come back and we'll walk through the standard form for each. But I want to take each of these zeros separately and write them as factors. And so this is going to be x plus 3 and x plus 3. And of course you could write x plus 3 with the squared outside of the parentheses, or just x plus 3 times x plus 3. And in this next one, the 7 gives you x minus 7, but then lost my place here. This negative 2i, positive 2i is a little bit awkward. So let's take a look, and again, think backwards here. If I am giving you x squared plus 4 equals 0, and you're to solve that, x squared equals negative 4, take the square root of both sides. That's where your imaginary answer comes from, is the square root of a negative. And remember that when you take the square root, you have to do both the positive and negative square root. So in this case, x equals plus and minus 2i, which is what we're looking at here. And so the x squared plus 4 is going to be your factors, or your linear factor. That's not linear, but your factor there. And so that's going to be x squared plus 4. Excuse me. And then this next one, x minus 1, x plus 4, and x minus 4. And in this next one, be careful. The 7, straightforward, gives you x minus 7, just like it did in part B. But these zeros here, each of them is an x. So if this is x and this is x and you're multiplying, then that whole thing is going to be x squared times x minus 7. Now, excuse me, in this first, to get the standard forms, in this first one, you want to FOIL, and that's first x times x is x squared, outsides 3 times x, insides 3 times x again, and lasts 3 times 3 is 9, and you're going to need to simplify the middle two terms because they're like terms. Your standard form is going to be x squared plus 6x plus 9. Now for part B, you're going to FOIL again, but be careful because you've got that x squared. And so when you FOIL, x squared times x is x cubed. The outsides is plus 4x. The insides, minus 7 times x squared. And the lasts is negative 7 times 4, which is minus 28. But this is not in standard form because I have the x before the x squared. So when I rewrite the answer, I'm going to write x cubed minus 7x squared, keep that minus with the 7, plus 4x minus 28. Now for part C, I'm going to do my work off to the side here. Remember that when you're multiplying 3 things, 1, 2, 3, you can only multiply 2 at a time. So I'm going to start by using FOIL with x minus 1 times x plus 4. So I'm going to take x minus 1 times x plus 4, and I'm going to FOIL that. And I get x squared plus 4x minus 1x, and then minus 4, which is x squared plus 3x minus 4. And then I want to take that whole thing and I want to multiply it by the x minus 4. So I'm going to take that and I'm going to multiply it by x minus 4. If you can use whatever method you know how to multiply a bigger polynomial times a binomial. You know that I like to do it this way, x squared plus 3x minus 4 times x minus 4. X times x squared is x cubed. X times 3x is 3x squared. X times minus 4 is minus 4x. Negative 4 times x squared is minus 4x squared. Negative 4 times negative 4 is plus 16. And I definitely forgot something there. Again, my apologies. Negative 4 times 3x is minus 12x. And negative 4 times negative 4 is plus 16. That looks right. Notice that I've lined up the like terms. So the ones that have a 2, the ones that have just x. Okay, and when I add or combine like terms, I get x cubed minus 1x squared minus 16x and then plus 16. And that's what I'm going to write over here. x cubed minus x squared minus 16x plus 16. And in this last one, I'm just going to distribute x squared times those two terms, and I get over here x cubed minus 7x squared. So for this section of the review guide, what I want you to do is think about the degree of a function in relationship to how many solutions it has, and whether the solutions are real or imaginary, and what the multiplicities of the solutions are. So let's start by talking about degree. You can only figure out the degree of a function or of a polynomial function by looking at the equation to know for sure. And when you look at the equation, you want to look at the biggest exponent in the equation, and that's going to be the degree of your function. And so let's say that this first one is degree 3, and this next one is degree 4. And this next one is degree 2, and this next one is degree 4. The number of complex solutions equals the degree. Remember that complex is both real and imaginary solutions, so it includes both. And so you're going to literally write the same numbers here, that if it's degree 3, then there's 3 complex solutions. They might be real, they might be imaginary, but there's 3. If it's degree 4, you've got 4 complex solutions. If it's degree 2, you've got 2 complex solutions. And I'm running out of colors, but if it's degree 4, again, you've got 4 complex solutions. All those numbers should be equal to each other in those 2 rows. But in order to decide how many real solutions there are, you need to graph it. So make a little note to yourself on that section that you want to draw the graphs of each. And so here, for that first one, pause the video for a second, grab your graphing calculator or Desmos in your phone if you're at home. Remember that you're going to need to be able to do these problems on the TI graphing calculator in class during the test. But Desmos is a fabulous app. It's free on your phone. Or on your computer or on your tablet, and it makes excellent graphs, and it will be incorporated into the SOL this year. So anyway, when you graph this first function, you should end up with a graph that looks kind of sort of like this. Now remember that the number of real solutions is how many x-intercepts it has. And so in this equation here, part A, there's going to be one real solution. It's not a double root. And if there's one real and you're supposed to have 3 altogether, that means that 2 of them are imaginary. And remember that what you're looking for is for this number plus this number to add up to that number of complex solutions. Now, when you graph this next one in your calculator, again, pause the video for a minute and go ahead and type that into your calculator or into Desmos. And what you'll find is in your graphing calculator that it goes like this and it goes like this. Well, it doesn't really matter as far as solutions go, what's going on down here or up here. That doesn't really matter. Because really what you want to be looking at is the x-intercepts. In this graph, I see 2 x-intercepts. And so that means that there's 2 real solutions. Neither one of them is a bounce, so there's no double roots. And if there's 2 reals, and I want there to be 4 complex solutions altogether, that means that there's 2 imaginary. Because remember that the number of real solutions plus the number of imaginary solutions should add up to the degree or the total number of complex roots. Now, your graph for C is actually going to look kind of similar to your graph for B. So when I graph C, I kind of get something that looks a little bit like this, and so we're looking at those x-intercepts. There are two of them. But this time, because it is only a second degree function or polynomial, that means that both of those real solutions are all of the solutions. Neither one of them is a bounce. 2 adds up to 2, and so there's no imaginary solutions. And remember that your number of real solutions and your number of imaginary solutions should add up to the number of complex solutions. So 2 plus 0 is 2 in this problem. And then in this last graph, you can see a little bit more of it in the graph screen. When you graph that one, it kind of ends up looking like this. And again, there's 2 real solutions. And so there's 2 real solutions. Neither one of them, I don't know why I have that column for double roots there. If there's 2 reals, there need to be 2 imaginaries, so that 2 plus 2 adds up to 4. And this next problem gets a little bit more at the heart of what I'm asking for, because it's asking for the number of real and non-real, or in other words, non-real means imaginary. Well, the total number of roots should add up to 3, because that's the biggest exponent. And I'm going to need to draw a graph of this to see how many reals based on how many x-intercepts there are. So when I graph this one, I end up getting a graph that kind of looks like this, and there's only one x-intercept. So there's only one real solution, but because there's 3 solutions altogether, 2 are going to be imaginary or non-real. Now, in these 3 problems here, these graphs, what we're getting at is not so much that you draw the exact graph from the points in the calculator, but that you're looking at the end behavior and the zeros. And it says there to emphasize the zeros. So based on this equation, you know that there's a 0 at x equals 0, at x equals 2, and at x equals negative 3. So I'm going to go ahead and put those points on the graph. X equals 0, x equals positive 2, and x equals negative 3. And because I have 3 x's being multiplied, I know that this is a 3rd degree equation. So therefore, because it's degree 3, which is odd, the ends are going to be different. And because there's nothing multiplied at the beginning of any of these 3 factors that's negative, the right end is going to go up and the left end is going to go down. They're different because it's degree 3, which is odd, and the right end goes up because the leading coefficient would be positive if you multiplied those factors out. And so I want to kind of have this go up through that 0, and then down through that 0, and back up through that 0 again. And your graph would look somewhat like that. For B, notice that this piece of it that's squared, that is going to be a double root or a bounce on the graph. So here you have x equals 0, a bounce at x equals negative 3, and then x equals negative 5. Because there are, because of this squared here, you're going to end up with an extra count toward your degrees. So it's x, x, another x, and x. So the degree here is 4, which means that the ends are going to be the same. And again, there's nothing negative being multiplied through the beginning of each of those factors, and therefore your right end is going to go up. And if the ends are the same, then both ends are going to go up. Remember to emphasize the zeros. So we're going to have a 0 at x equals 0, a bounce at x equals -3, and then another 0 at x equals -5. And I'm going to kind of adjust where I have those ends that I drew. Just remember that both ends are going up. So if I start over here, I'm going to come down through here, bounce there, and then go up there. And now I've got both ends going up with the bounce at -3. And in this last one, I've got 2 bounces. I've got double root at x equals -2, a double root at x equals +1, and a single root at x equals +3. And so make sure you know that there's going to be a bounce there and there. I'm going to put those numbers on the graph. Bounce at -2, bounce at +1, another root at +3. And if I count the degree, x times x times x times x times x, that's going to be degree 5. So degree 5. And so the ends are going to be different. And because there's, again, nothing negative multiplying through the beginnings of any of those, then your right end is going up. And if the ends are different, then your left end is going down. So if you have a bounce at -2 and a bounce at +1, it's kind of going to do this, and then this. The ends are still different. The right end goes up, and you've got a bounce at -2, a bounce at +1, and a single root at +3. In number 28, if you're looking for the correct factored form, you want to start by looking at the x-intercepts. You've got an x-intercept at -1 and an x-intercept at +2. That means that you should have a factor at x minus 2 and a factor at x plus 1. And the one that reflects that down here is letter C. Notice that in letter C you have this negative, actually all of them have this negative out in front, and that's what gives the graph the downward opening. And in this graph over here, it asks about double zeros, and be careful because this doesn't actually bounce on the axis. It goes below the axis and then comes back up above the axis. So no, there's no double zeros in 29. Now, in number 30, what you're going to be doing is factoring these functions and or equations or expressions, and then finding the zeros based on what you factored. So the first thing that you want to remember to do is get everything equal to 0. And so I'm going to start by subtracting 18x from both sides. You always want to try to keep your leading coefficient positive if at all possible. And then you have to remember to check to see if there's a GCF, and in this case there's a GCF of 2x. And so I'm going to divide each term by 2x. And when I take 2x out of 2x squared or 2x cubed, I end up with just x squared left. When I take 2x out of negative 18x, I'm left with negative and then 9, but I've divided out the x, so there won't be an x in that. Then x squared minus 9 is also factorable. I have to keep that 2x, And then x squared minus 9 is x plus 3 times x minus 3, and all of that equals 0. Then you take each of those factors and set them separately equal to 0. And then solve each of those equations. So here x equals 0, here x equals negative 3, and here x equals positive 3. So the factors are 2x, x plus 3, and x minus 3. And the zeros are x equals 0, minus 3, and plus 3. So again, for letter B, we want to get all of the terms on one side of the equation so that the whole thing is set equal to 0. And so I'm going to subtract the 36 from both sides, and I get x to the 4th plus 5x squared minus 36 equals 0. And what you want to think here, look at the x to the 4th and look at the x to the 4th and look at the x squared. And because x squared is x to the 4th, let's rethink this problem and think, when you're factoring, x squared plus 5x minus 36. So if you want to factor that, remember that you look at negative 36 as a product, or two numbers multiplied, and positive 5 as a sum, which is two numbers added. And you want the same two numbers that multiply to negative 36 and add to 5. And that's going to be positive 9 and negative 4. So if I were going to factor the expression that starts with x squared, I would get x plus 9 times x minus 4. And so all we're going to do is change anything that was x in this expression to the x squared in the actual expression that we're factoring. And so when you factor this, you get x squared plus 9 times x squared minus 4. All of that equals 0. And so you should notice that x squared minus 4 can be factored further. X squared plus 9 cannot. So we're going to keep x squared plus 9 and not factor that. But factor x squared minus 4, which becomes x plus 2 and x minus 2. And that's all really, again, just to kind of stress the fact that we can factor x squared minus 4 because it's subtraction. We cannot factor x squared plus 9 because it's addition. But then you're going to take each of those factors and set them equal to 0. And so x squared plus 9 equals 0, x plus 2 equals 0, and x minus 2 equals 0. And then solve each of those. Subtract 9 here so that you get x squared equals negative 9. And then when you take the square root of both sides of this, two things that you need to remember. First of all, when you take a square root to solve an equation that has an x squared in it, you need to use plus or minus. And then because of the negative number inside the radical, your answer has to be imaginary. So if it were just the square root of 9, it would be plus or minus 3. But because of the negative 9, it's going to be plus or minus 3i. And then x plus 2 equals 0 becomes x equals negative 2. x minus 2 equals 0 becomes x equals positive 2. And remember that you kind of want to check the degree of the equation. In the original expression is 4. And so you want to have 4 solutions. And so here I have plus 3i, minus 3i, negative 2, and positive 2. There's my 4 solutions. And so the factors here are x squared plus 9, x plus 2, x minus 2, and then the zeros are x equals plus and minus 3i. And you could put plus and minus 2, or you could write them out separately too, and negative 2. The order there does not matter. So on the next page, 2 more problems that are factoring by, or solving a polynomial equation by factoring. So in letter C is already all set equal to 0, and so you don't need to move anything to any other side of the equation. But when I look at this, I see that I have x to the 4th here, x to the 3rd here, and x squared there. And so I have at least x squared in each expression. And so I'm going to factor out a GCF that is x squared. And so when I factor out the x squared inside the parentheses, then I have x squared plus 4x minus 5 equals 0. And now I need to factor what's inside the parentheses. It can be factored further. Bring down the x squared that was your GCF in the first step. And then remember here that negative 5 is the answer to a multiplication problem, and positive 4 is the answer to an addition problem. So 2 numbers that multiply to negative 5 and add to positive 4 are positive 5 and negative 1. So x plus 5 and x minus 1, all of that equals 0. You're going to set each factor equal to 0. So x squared equals 0, x plus 5 equals 0, and x minus 1 equals 0. Now here, remember that you've already got everything equal to 0, but this is 2 zeros. You're basically thinking x equals 0 and x equals 0 for each of the x's that's multiplied here. In the next one, you've got x is equal to negative 5, and in this last one, you've got x is equal to positive 1. And again, you want to kind of count your solutions. It's a 4th degree expression or equation. 1, 2, 3, 4 solutions. So your factors are x squared, x plus 5, and x minus 1. And your zeros are 0, 0, negative 5, and positive 1. And of course you're thinking, she forgot to write x equals. Yep, she forgot to write x equals. So the zeros are x equals 0, 0, negative 5, and 1. My apologies. And so the 4th problem where you're going to be factoring to solve, remember that if you have f of x, the f of x form of a polynomial function, you can replace that f of x with a 0 if you're solving. And so 0 equals 9 x to the 3rd minus 18x squared minus 4x plus 8. And then you notice hopefully that there are 1, 2, 3, 4 terms, and when you're asked to factor and you're given 4 terms, that you do grouping. And so grouping says that I'm going to kind of look at 2 terms at a time. So I'll start with the 9x cubed minus 18x squared, do a GCF of those 2 terms, and then I'll look at negative 4x and plus 8 and factor a GCF out of those 2 terms. Now keep your 0 equals over here. When I look at just the 9x cubed minus 18x squared, I see that 9 comes out of both of those terms and x squared comes out of both of those terms. And what I'm left with is just an x and minus 2. And what I like to do when I'm working out these problems, it's hard to do on the video, but I actually visually cover up the 2 terms that I'm not working with. So I'm just looking at the 9x cubed minus 18x squared and the answer 9x squared times x minus 2. And then once I've done that GCF part of the problem, I look at just the other half of the problem, and I literally take a piece of paper and cover it up and look at minus 4x plus 8. Remember that when you are factoring a GCF, the GCF is going to have the same sign as the first term. And so in this case, we're going to factor out a negative. And 4, excuse me a second. So you're going to factor out a negative, and 4 goes into both 4 and 8. When you factor out a negative, your signs change, and so this is going to be x minus 2. So that plus here became a minus down here. So once again, what you got when you factored the pink part was this. Excuse me, and what you got when you factored the green part was this. Then the next thing that you're going to do is you're going to take the 2 GCFs that you found, the 9x squared and the minus 4, and those are going to become the other binomial. So now you have 0 equals, take the 9x squared and the minus 4 and multiply that times x minus 2. Now, hopefully at this point, you can see that 9x squared minus 4 can be factored again. And so now I have 3x plus 2 times 3x minus 2 times x minus 2. And in case you missed that, the reason that I can factor 9x squared minus 4 is because 9 and x squared and 4 are all perfect squares and they're being subtracted. So the square root of 9 is 3, the square root of x squared is x, and the square root of 4 is 2. And then in my answer, I just have one of them is plus and one of them is minus. So the factors that I'm going to write down here are just those 3 factors, 3x plus 2, 3x minus 2, and x minus 2. And then I have to solve for each of those set equal to 0, and I kind of didn't leave myself enough space here. So let me go up and do that off to the side. I have big, huge margins, and you don't. Sorry. So I've got 3x plus 2 times 3x minus 2 times x minus 2, and that whole thing is equal to 0. So I'm going to set each of them equal to 0. 3x plus 2 equals 0, 3x minus 2 equals 0, and x minus 2 equals 0. Solve each of them for x. So this is 3x equals negative 2. So x equals negative 2/3. This is going to work similarly. 3x equals positive 2, so x equals positive 2/3. And then for this one, x is equal to positive 2. And so your 3 zeros are positive and negative 2/3, and x equals 2. And again, make sure that you see that because the original equation is a third degree equation, you're going to have three solutions: negative 2/3, positive 2/3, and positive 2. And let me write those down here. Now, 31 is exactly like number 30. All four problems in number 30 asked you to solve by factoring. 31 doesn't say to factor, but that is one way that you can solve it. For me, that's going to be the easiest way. If you wanted to, you could also graph this. If you wanted to graph it, you would just put the y here, y equals all of that. And then you can look for the zeros that way. I'm going to go ahead and factor this. So I'm going to say 0 equals 16 x cubed minus x. So 0 equals, and then I see the GCF is x. So it's going to be 16x squared minus 1. And then I see perfect squares here with the subtraction. And so that whole thing becomes, bring down my original GCF, and I get 4x plus 1 times 4x minus 1. Now, if my factors are each set equal to 0, I've got x equals 0. I've got 4x plus 1 equals 0. And 4x minus 1 equals 0. So 4x equals negative 1, or x is equal to negative 1/4. Or 4x equals positive 1, and x equals positive 1/4. And so my answers are x equals 0, positive 1/4, and negative 1/4. Remember the wording here, just to make sure that you see that. X-intercepts, solutions, roots, all of those are going to be found, can be found using similar methods. So from number 32 to the end of this page, we get back into some of the synthetic division. But instead of saying divide, find a quotient, what we're connecting here is that division is connected to factors or solutions or roots of an equation. So, for example, what I'm saying is that if x minus 3 is a factor of this big polynomial, then x minus 3 equals 0, or x equals positive 3, is going to divide evenly into the polynomial without a remainder. So you're going to divide and look to see if there's a remainder. So let's start with the coefficients, and I've got a cubic function, so x cubed, x squared, x, and no x. And so I don't need to use any placeholder zeros. When I'm dividing, I'll say 3, negative 2, positive 3, and negative 4. And I'm dividing by 3. Bring down the 3, multiply. 3 times 3 is 9. Negative 2 plus 9 is 7. Multiply again. 7 times 3 is 21. 3 plus 21 is 24. 24 times 3, grab your calculator, multiply. 24 times 3 is 42. Negative 4 plus 42 is 38. And since the remainder here, remember that 38 is your remainder, since the remainder is not 0, then x minus 3 is not a factor. And just take a look real quick at the directions here. The directions say, show whether this is a factor of that. That's really a yes or no question. Is it a factor? Is it not a factor? We've decided it's not a factor, but remember that it says use division to do so, and so you need to use division and show your division in order to prove that that's not a factor. So let's do that same process again with number 33. And again, we're saying, okay, we want to see if this is a factor of this. Yep, that was my clock that I stopped the video for, and you probably heard the first few notes, but it's better than Baby Shark, which has been stuck in my head for the past couple of hours. Why, I don't know. But you don't want me to sing it for you. So anyway, we are going to use division to show whether x minus 4 is a factor of that polynomial. Remember that your answer is basically going to be yes it is or no it isn't, and we're going to use division as proof. So you have to show the division, but you also have to answer it with a yes or no. Now, I see that I have a third degree polynomial, but I'm missing the last term that has no x. So I'm going to need to use a 0 as a placeholder. So I've got 1x cubed minus 3x squared minus 4x, and then 0 holds that last place. And I'm dividing by, remember that you want to set that equal to 0. I'm dividing by positive 4. And so I bring down the 1. 1 times 4 is 4. Negative 3 plus 4 is 1. 1 times 4 is 4. Negative 4 plus 4 is 0. 0 times 4 is 0. 0 plus 0 is 0. So because the remainder is 0, then you can say yes, x minus 4 is a factor of that polynomial. Now, for problems like 34 and 35, you're going to use both division and factoring to solve a polynomial. If the problem says this is a factor, given that there is a factor that is x plus 2, or given that one of the factors is x plus 2, you know that when you divide by negative 2, remember x plus 2 equals 0, so x equals negative 2. When you divide by negative 2, your remainder will be 0 because this is a factor. So I'm going to start my division here. I've got a third degree polynomial. There's no missing terms. So I'm going to divide 1, 3, negative 10, and negative 24. And I'm dividing by negative 2. And remember that your remainder, the number that you get in that very last spot, will end up being 0. So here's my division process. Bring down the 1. 1 times negative 2 is negative 2. Add 3 plus negative 2 is 1. 1 times negative 2 is negative 2. Negative 10 plus negative 2 is negative 12. Negative 12 times negative 2 is positive 24. We get 0 as the remainder, like we knew we would. And then this polynomial that's your quotient, x squared plus 1x minus 12, that you're going to factor, because it says use division to find all the zeros. Once you get down to a quadratic, you're going to want to factor the quadratic so that you can find the rest of the zeros. This is one of your zeros. And then factor x squared plus x minus 12. And I get x plus 4 times x minus 3. I'm going to also include that x plus 2 here and set the whole thing equal to 0. Then each of the factors equal to 0. X plus 2 equals 0. X plus 4 equals 0. And x minus 3 equals 0. X equals negative 2, negative 4, and positive 3. And again, just to double check, your original function was third degree, and you've got 3 solutions. Let's try a similar process in number 35. Look at the wording of the problem. Use division and then factoring to find all the zeros. You're told that x minus 3 is a factor. If x minus 3 is a factor, you're going to divide by x equals positive 3, and you know that the remainder is going to be 0. And you're going to divide into this polynomial here. It's a third degree polynomial, and I see x cubed, x squared, x, and a term without an x. Therefore, I know that I won't have any 0 placeholders. So my division will look like this. I've got 4, negative 8, negative 15, and positive 9. And I'm dividing by positive 3. Bring down the 4. 4 times 3 is 12. Negative 8 plus 12 is 4. Again, 4 times 3 is 12. Negative 15 plus 12 is negative 3. Negative 3 times 3 is negative 9. Negative 9 plus 9 is 0. We knew that that was going to be the remainder because we already knew that was going to be the remainder because we already knew that positive 3 was a or x minus 3 or x equals positive 3 is a factor. But now I'm going to take the quotient that I have right here and and I'm going to factor that 4x squared plus 4x minus 3. And I'm going to factor that, drop my pen. Okay. And for those of you that are good with the box method, go ahead and fast forward a minute or so. But I think what I want to do is walk through the box method on this problem off in the margin. So either bear with me or learn the box method or fast forward. But here we go. Off in the margin, I am going to factor 4x squared plus 4x minus 3. And now remember that with the box method, you take the first coefficient and multiply it by the last coefficient. And so for this, 4 times negative 3 is negative 12. And then you want to look for two numbers that multiply to negative 12 and add to positive 4. And those two numbers are going to be positive 6 and negative 2. Positive 6 times negative 2 is negative 12. And positive 6 plus negative 2 is positive 4. And then I'm going to make a box that's 2 by 2. So my 2 by 2 box. And in the top corner and the diagonal bottom corner of the box, I'm going to put the 4x squared and the minus 3 like that. Then I'm going to go and grab the 6 and the negative 2, and I'm going to put x's with them. And I'm going to put those in the other two corners. And it doesn't really matter which goes in which corner. As long as you had put the 4x squared and the negative 3 in those other two boxes, the 6x and the minus 2x don't matter. And then the next thing that you want to do is do 4 GCF problems. So the 2 GCFs going across are going to be 2x. And remember that when you're leading, or your first number that you're taking GCF is negative, your answer is going to be negative. Nothing else goes into 2x and 3, so it's just going to be -1. And then I'm going to do 2 vertical GCFs. And so in this case, the GCF of 4x squared and -2x is 2x, and the GCF of 6x and -3 is going to be just 3. And so my answers here are taken from those GCFs, and I have 2x plus 3 from the bottom and 2x minus 1 from the side. And so that's how you use the box method to factor this. Now, hopefully those of you who fast forwarded are back with us. And let me write this out then. 2x minus 1 times 2x plus 3. And then I'm going to go back up and I'm going to snatch that factor from the beginning of the problem, the x minus 3, and I'm going to include that in there and set the whole thing equal to 0. And then set each of the separate factors equal to 0. So 2x minus 1 equals 0. 2x plus 3 equals 0. And x minus 3 equals 0. Solve each of these for x. 2x equals 1, so x equals 1/2. 2x equals -3, and so x equals -3/2. And then x equals +3, which we had already known. And so my solutions, or the zeros of this equation, are 1/2, -3/2, and +3. Now, 36 is technically the last problem, but stay tuned because I also am going to do some factoring that's not in your packet. But if you need practice with the factoring of cubes and the grouping, I'm going to put some of that on a separate page, and I'm going to attach it to the end of this video. But let's finish this last problem. So number 36 says that this function, when you graph it, you get this graph. And so by looking at that graph, you know that this is one of the zeros, or one of the solutions of that function. And so if this is 1, 2, 3, this is 4, that means that x equals 4, or let's say the factor x minus 4 is a solution, or x minus 4 is a factor. So the problem says use division to divide by the 0 that I just found, and then factor to find the other ones. So let's start with division. I'm going to take this 4th degree polynomial, and I'm going to divide by that solution, x equals 4. I've got x to the 4th, x to the 3rd, x squared, x to the 1st, and no x. So it's 1, 3, -27, +3, and -28. I don't need any 0 placeholders. And I'm dividing by 4. Bring down the 1. 1 times 4 is 4. 3 and 4 is 7. 7 times 4 is 28. Negative 27 plus 28 is 1. 1 times 4 is 4. 3 plus 4 is 7. 7 times 4 is 28. And negative 28 plus 28 is 0. And you knew that that was going to work out to give you a remainder of 0 because of this. All of that tells you that your remainder should be 0. And then the quotient that you get here, because we started with x to the 4th, our quotient is going to be x to the 3rd. X to the 3rd plus 7x squared plus 1x plus 7. Now we need to factor, we're going to factor this. And because it's 4 terms, we're going to factor by grouping. So I'm going to take that expression, let me rewrite it here for you, x cubed plus 7x squared plus x plus 7. And when I'm grouping, I do 2 terms at a time. So I'm going to look at these and find a GCF, and I'm going to look at these and find a GCF. So the GCF here is x squared, and then I have x plus 7. And then for the green, there's no GCF, so I'm going to write 1 plus 1 times, and then x plus 7. And then remember that when you're factoring by grouping, you take the 2 GCFs that you found, and those become the binomial for your answer. So x squared plus 1 times x plus 7. So now you've done here the synthetic division and you did the factoring, but you have to still find the zeros. So the directions ultimately say find the zeros. And so I know that because it's a 4th degree polynomial, there's 4 solutions. So I'm going to take these, set it equal to 0, x squared plus 1 equals 0, x plus 7 equals 0. So here x squared equals negative 1. So x is going to equal plus or minus the square root of negative 1. And remember that that means x equals plus or minus I. And here x equals negative 7. So this is 2 solutions, plus I and minus I. This is 1 solution, negative 7. And so if you want to write all 4 solutions, start with that positive 4 from the graph. I'll grab the negative 7 next, and then the plus and the minus I, and those are your 4 solutions. Now, like I said, you will have questions on your test that are going to be factoring some difference of cubes and grouping. And we've already done some grouping in this review guide, and I don't have anything in the review guide so far that is some difference of cubes. Really, the review guide, the homework part of it, is what you've just done in this packet, in this super long, I apologize for the length video. But I do want to go through a couple of practice problems of each type, the cubes and the grouping, for those of you that want the extra practice. So if you're done with the homework and you want to be done, go ahead, turn off the video, and go ahead and continue studying for your test. But if you want a little bit more practice with the grouping and the factoring cubes, then go ahead, grab a scratch sheet of paper, and I'm going to give you, I think I have 5 problems worked out that I'd like to go through with you. So let's start with problems that have cubes, and remember that you can factor cubes using a sum or a difference. So whereas with squares, you can only factor perfect squares if it's perfect square minus perfect square. but with cubes it's either plus or minus. So for example, I could say to you, factor x cubed plus 8. And the first thing that you want to notice is that x cubed is a perfect cube, 8 is a perfect cube, and kind of keep track of the sign that's initially in the beginning. And so my thinking here is that the cube root of x cubed is x, and the cube root of 8 is 2. And so the first part of my answer is going to have an x and a 2, and I'll worry about the signs in a minute. And the next part of my answer is going to be a trinomial, or have 3 terms. And in order to figure out those 3 terms, I'm going to take the x and the 2 that I wrote a minute ago, and I'm going to write each of them 3 times. So I'm going to write x, 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 2, 2, 2. And then I'm going to take those 6 things that I've written and circle 2 at a time, and then multiply. This one's x squared, this one's 2x, and this one's 4. And those 3 things are going to be the 3 parts of my trinomial over here. So now I have x squared, 2x, and 4. And then I'm going to use the acronym SOAP. And SOAP stands for same, opposite, and always positive. So I look at my plus sign here, and my first sign in my answer is going to be the same, plus. Then the next sign in my answer is going to be the opposite, minus, and the last sign in my answer is going to be always positive. And so my answer to, let me just kind of visually separate this for you. When I say factor x cubed plus 8, your answer is going to be x plus 2 times x squared minus 2x plus 4. So let's walk through another example, number 2. Let's factor 1 with a minus sign this time. So how about factoring x cubed minus 125? So when I look at this one, I see that the cube root of x cubed is x. I see that the cube root of 125 is 5. And that I'm starting with a difference or a subtraction. So in my answer, I'm going to have x here, 5 here. I'll worry about the signs later. And then to fill in the other part of my answer, I'm going to take those cube roots that I found. The x cubed is x and the 125 is 5, and I'm going to write each of them 3 times. So x, 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 5, 5, 5, and then I'm going to circle them 2 at a time and multiply. So I get x squared, 5x, and 25, and those are the 3 things in the trinomial here. X squared, 5x, 25, and then I'm going to use SOAP. I've got a subtraction here, so the first sign is the same, the next sign is the opposite, and the last sign is always positive. Now, of course, these problems can get trickier, so let's try one that's a little bit more difficult. Let's say that I ask you to factor 216 minus 8z to the 3rd power. Well, when I look at this, I know that 8 is a perfect cube. the cube root is 2. And I know that, drop my pen again, z cubed is a perfect cube, and that the cube root is z. So the cube root of 8z cubed is 2z. But I'm not really also sure about the number 216. I don't know if that's perfect cube. Hint, it is. But if this was a test or a homework assignment and you don't know, you're going to grab your calculator, and on the graphing calculator, you press math. And when you've done that, you look down that list there, and it's the 4th thing on the list, so math 4, and it gives you a little cube root thing there, and you can type 216, hit enter, and it'll tell you that it's 6. And so the cube root of 216 is 6. Now keep your answer in that order. So for the first part of my answer, I'm going to have a 6 here and 2z here. Then I'm going to take the 6 and the 2z, and I'm going to write each of those 3 times. 6, 6, 6. And watch how this works here. 2z, 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 and I'm going to circle them 2 at a time, 2 at a time, 2 at a time, and then multiply. 36, 12z, and 4z squared. Now keep those in that order. The 36 first, then the 12z, and then the 4z squared. Let me make that a little bit better here. And then my original sign is minus. And so in my answer, same, opposite, always positive. Now I also want to talk about factoring by grouping. Let me change colors here. So you always do this when you start with 4 terms. So let's say, for example, that I say to you, factor the polynomial x cubed minus 3x squared plus 5x minus 15. So what you want to do then is look at 2 terms at a time. I'll start with the x cubed minus 3x squared, and then later I'll look at the 5x minus 15. And you want to find the GCF of each pair of terms. So x cubed and minus 3x squared, the GCF is x squared, and that leaves me with x minus 3. And then the last 2 terms, the 5x and the minus 15, a positive 5 comes out, and I'm left with x minus 3. And then the last thing to remember is that the 2 things that you used as the GCFs make your binomial in your answer. So x squared plus 5 times x minus 3. Let's do one more factor by grouping problem. So let's say that I ask you to factor 4x cubed plus 28x squared minus x minus 7. So make sure that you know exactly what I'm talking about when I say 4 terms. I just underlined 4 separate terms, and that's the only way that you can do factoring by grouping. So I'm going to start with those first 2 terms and then separately look at the last 2 terms. So in those first 2 terms, I see that 4 divides into both and x squared divides into both. And that leaves me with x plus 7 here. And then in the 2 that I underlined in green, remember that you always want to use the sign from the very middle term, or that term at the beginning of the green part. And so now you're going to say, okay, I'm going to factor out a -1. Nothing else goes into both x and 7, so it's -1. But then that changes the signs on the x minus 7 in there, and it becomes x plus 7. So now I'll use the 4x squared and the -1, and that'll be my one binomial, 4x squared minus 1, and then x plus 7 will be the other binomial. And your 4x squared minus 1 can still be factored because 4 is a perfect square, x squared is a perfect square, and 1 is a perfect square. And so that'll be 2x plus 1 times 2x minus 1, and then x plus 7. And there you have factored that expression. Baby shark.